The contents of a closed box in each of the following illustrations represents a system, and the arrows show the changes to the system in some process. The lengths of the arrows represent the magnitude of heat and work. A. Which process is endothermic? Well, I is the only one where heat is going into the system. Endothermic, the surroundings gives heat to the system. So the system is gaining heat, and the surroundings is losing heat. B, for which process, if any, is the internal energy net less than zero? I mean, you have a negative value, right? The system's losing internal energy. Well, I look at all these, right? The magnitude in I, the magnitude of W is greater than Q, so you got more work going in than heat coming out. In II, you only have work going in. And in 3, or III, you've got more heat going in than work coming out, so none of the above are you losing internal energy to the system. They're all gaining. So for which process does, if any, does the system have a net gain of internal energy? They all do. All right, so they're all, the net for all of these is an increase in internal energy. 5, imagine you're climbing a mountain. Is the distance you travel to the top of the top a state function? Why or why not? All right, so here's our peak. If I take pathway red, this is costing me a certain amount of work, right? So if you follow the dotted line, right, this is how much work I have to, represents how much work I have to do to go from the lower elevation to the upper elevation. If I take pathway blue and go this way, and then compare the two pathways, I'm actually doing more doing more work following route red than following route blue. So what this shows is that work is not a state function, it's pathway dependent. Depends how many steps you take, in terms of going back and forth to get to the top. Whereas the change in elevation is the same whether I go the red route or the blue route. It's pathway independent. So change in elevation is a state function, whereas the pathway is not a state function. It's pathway dependent. What is meant by the term system in thermodynamics? Well, the system is what we study, right? So for chemistry, it's the chemical reaction. So is the chemical reaction losing heat or gaining heat? What is a closed system? A closed system is one where you're not exchanging either material or heat with the surroundings. What do we call part of the universe that is not the system? Well, if it's not part of the system, then it's the surroundings. So system plus surroundings equals the universe. So if the system is losing heat, that means the surroundings is gaining heat and vice versa. 45. When solutions containing silver ions and chloride ions are mixed, silver chloride precipitates. Right? We know this from our solubility rules. And you release 65.5 kilojoules. Calculate the delta H if 0.45 moles of silver chloride is produced during this reaction. All right, so this is per mole, right? For every mole, according to the thermochemical equation, for every mole of silver chloride, you're releasing 65.5 kilojoules. So that's our conversion factor to go from moles to kilojoules. So we don't have a mole. We've got less than half a mole. So we're going to have less than 65.5 kilojoules being released. Calculate the heat for the production of 9 grams of silver chloride. So same thing, except we got grams, right? So the first step is get out of grams, get to moles using molar mass. Now I can use the new conversion factor to go from moles to how many kilojoules were released. So that's the new thing with thermochemical equations. We have a way of equating the coefficients in the equation to heat change. C, calculate delta H for the production of 9 grams. Oh, we did that. Sorry, C. Calculate the delta H when 9.25 moles of silver chloride dissolves in water. All right, so dissolving in water is the reverse of precipitating. So if I turn the reaction around, right, instead of talking about silver ions and chloride ions coming together to form a solid, if we turn it around, we talk about the solid being taken apart and going into solution, then we're just changing the sign on delta H. If I reverse the direction of the reaction, I change the sign on delta H, and I get my conversion factor to go how much heat would be required in order to get this many moles of silver chloride to dissolve. So an endothermic process if you want it to dissolve. A 2.2 gram sample of quinone is burned in a bomb collimator whose heat capacity is 7.854 kilojoules per degree Celsius. The temperature of the collimator increases 23.4 degrees Celsius. From 23.44 degrees Celsius to 30.57 degrees Celsius. What is the heat of combustion per gram of quinone per mole of quinone? All right. So when we're using a bomb collimator, it's strictly how hard it is to heat up the bomb times the temperature change, right? In this way, right, we convert from degrees Celsius to kilojoules. So for this temperature change, we're releasing 56 kilojoules, and what we burned was 2.2 grams. So if I divide grams into kilojoules, I get kilojoules per gram. If I want kilojoules per mole, I use the molar mass of quinone to get to kilojoules per mole. I think I messed up. I didn't do the grams. But just divide grams into kilojoules, and you get kilojoules per gram. So I did to moles. All right, from the enthalpies of reaction, calculate the delta H for the reaction of ethene with fluorine. All right, so we've got 2 moles of hydrogen fluoride being made, and I have 4 moles of hydrogen fluoride coming out. So whatever I do to the chemical equation, I do to the delta H. So I wanted to make these three, right, these 3 enthalpies of reaction look like the enthalpy of reaction that I want to get to. So I want 4 moles of HF coming out. So if I multiply that thermochemical equation by 4, multiply by 2, I multiply the delta H by 2. I want 2 moles of carbon tetrafluoride coming out. So I'd multiply the thermochemical equation for the formation of carbon tetrafluoride by 2, and I multiply the delta H by 2. Now I have 2 moles coming out. I want ethene going in as a reactant, not coming out as a product. That means I have to turn the reaction, the heat of formation of ethene around and turn it into a decomposition. And that means changing the sign on delta H. So now I'm ready. I've got everything where I want it, right? If I add everything together, the carbons and the hydrogens cancel, and I've got 2 and 4, that's 6 fluorines going in, 1 mole of ethene going in, 2 moles of carbon tetrafluoride coming out, and 4 moles of hydrogen fluoride coming out. So whatever I do to the equations, I do to the delta H, so just add the delta H's together, and I get the heat change. 3 sig figs. All right, given the data, we've got 3 thermochemical equations we want to make look like the last one, right? We want dinitrogen monoxide reacting with nitrogen dioxide to make 3 moles of nitrogen monoxide. So first things first, if I'm looking up at the top one, I'm going to leave that one alone because I've got nitrogen monoxide on both sides. I'm looking at the second thermochemical equation. I want nitrogen dioxide going in as a reactant. So that means turning the synthesis of 2 moles of nitrogen dioxide around, and I only want 1 mole going in. I don't want 2 moles, so dividing it by 2 so that I have 1 mole of nitrogen dioxide going in. I also want it reacting with dinitrogen monoxide. I've got 2 moles going in according to the thermochemical equation they gave me. So if I divide it by 2, then I'd have 1 mole going in. And that looks like it fixed it. At this point, if I add these together, I've got 2 halves of a mole of oxygen coming out. It's the same thing as 1 mole going in, so they'll cancel. And I've got 1 mole of nitrogen going in, 1 mole of nitrogen coming out. And look at that, the nitrogen monoxides got fixed. I've got 2 halves, which is 1, plus 2 is 3, and it comes out nice. So really, if you just focused on those particular reactants, it came out nice. And then if you add the thermochemical equations together to get the one you want, you add the delta H's together to get the answer. And that's the beauty of Hess's law. It doesn't matter how many steps you have. As long as you manipulate it to come up with what you want, get the reactants and the products in the right place, your delta H comes out right. 57. What is meant by the term standard conditions in enthalpy changes? Standard conditions for thermochem is 1 atmosphere pressure, 25 degrees Celsius, or 298 Kelvin. Standard conditions is going to be different later on when we talk about gases. B, what is meant by the term enthalpy of formation? Well, that's when we take elements and put them together and form a compound, right? 1 mole of the compound. What is meant by the term standard enthalpy of formation? Well, that's done at standard conditions. Yeah, duh. Why are the tables of standard enthalpies of formation useful? Well, because we can use them, right? These standard enthalpies of formation to figure out other heats of reaction or other heats of formation. What is the value of the standard enthalpy of formation of an element in its most stable form? Oh, right. So arbitrarily it was decided that elements were going to be 0, and we put these two things together that are 0, we look for the change, right? This is how we get enthalpies of formations for different compounds, by putting elements at 0 together to see what the change is. Write the chemical equation for the reaction, for the enthalpy change, standard enthalpy of formation for sucrose. All right, so I don't know how they wrote it so strange. I just want to create the definition of the heat of formation for sucrose. So I want 12 carbons going in, I want 22 hydrogens going in, and I want 11 oxygens going in. All right, so that'd be the same as 11 halves, right? And that's, let me go back, I messed up. And that'd be per 1 mole per 1 mole of sucrose being formed. So, 69. For each of the following, write the balanced thermochemical equation depicting the formation of 1 mole of the compound. Obtain the delta the delta H's of formation in table C. So if I'm going to write the heat of formation for nitrogen dioxide, I want half a mole of N2 going in, reacting with 1 mole of oxygen to make 1 mole of NO2. I looked up the delta H in the appendix C. For sulfur trioxide, I want sulfur reacting with 3/2 of a mole of oxygen, so I get 3 oxygens coming out the other side. Again, I could look up what the delta H of formation is. I can do the rest for sodium bromide and lead nitrate. Gosh, I'm quick at the thing today. I didn't get D in there. Damn it. Oh, we skipped D. We're moving on. Complete combustion of 1 mole of acetone liberates 1,790 kilojoules. Using this information together with the data from Appendix C, calculate the enthalpy of formation for acetone. All right, so one way that we can find heats of formation is to plug into the sum of the products minus the sum of the reactants, set it equal to the heat of reaction. All right, we know what the heat of reaction is for the combustion of acetone. We know what the heat of formation for oxygen is, and we can look up the heats of formation for carbon dioxide and water and plug them in and solve for the missing heat of formation. So when we add these up, we can find the heat of formation for acetone. 76, same thing. Calcium carbide reacts with water to form acetylene and calcium hydroxide. From the following enthalpy data and the enthalpy of reaction here, and Appendix C, find the heat of formation for calcium carbide. So I know what the heat of reaction is for this reaction. I can set that equal to the sum of the products minus the sum of the reactants, look up the known ones, and solve for the one I don't have. So another way to find the heat of formation is to plug into this permutation of Hess's law.